So a matrix made up of a bunch of aij's, being this A11, A1n, AM1, AMN. So this is m by n. But another way for us to look at this, and this was important to remember other ways of considering it, so I can look at a matrix as a rectangle of numbers. The whole purpose, originally we said, okay, matrices came into existence to study systems of equations. This was the coefficients. What are all the things that we can do with it? We can invert it and all these other sorts of operators. What we talked about it in particular was also to consider that a matrix is made up of a bunch of columns. And each of those columns had a name, vector, right? On the other hand, instead of looking at it as a bunch of columns, I could look at it as a bunch of rows. But each of those rows has its own name, vector, but it's called row vector to designate the differences between the two. Right? And the dimension is how many elements are there. But there's a reason why we use the word vector, knowing that matrices themselves and linear algebra and all the stuff being developed had another application associated with it that would be interesting, and how these things could work in application as well. And the other application of it is to consider space. Call him a vector, call him a row vector. I put space in quotes. All right, what is a space? Well, if I think of it kind of like the traditional space, when we think about the words that we have as examples of things like this, we could talk about, say, a one-dimensional space. So a one-dimensional space sits there, and when we look at it, it just simply means that you're existing on a line, and I can have values on this. We normally call them scalars, right? But in one-dimensional space, it really is, where are you, is the most important question. And you have this stuff, and if I'm going to ask you, where are you, there obviously needs to be an origin, because if you say, where are you, it's in relation to what? I can't answer that question. I am where I am. Give me an origin of some sort. So you have to come into the space and say, this is what I consider the center of, or some concept of it. And then when you ask me, where are you, where am I in association with this? Now, these are obviously quantities, right? We use this a lot. Like, oh, look, you have this much money. You owe me that much money. And we have applications of it. But it's actual things. Like I can sit there and say things like, oh, look, I have 1, 2, 3, 4. I have 5 dot dashes. And so when we go to position, and I may call this in a numeric sense 5, this thing itself is, obviously this thing has meaning where I go across it. Let's say it's a 4, right? What does 4 really mean? It means I have a 1, a 1, a 1, and a 1 that have all put together, and it calls a thing that I call 4. But I choose to give it a number representation to make my life a little bit easier. It's a psychological representation. I can simply say this, oh look, 4 people, 4 chairs, 4 inches. The 4 is the same thing. It talks about a cardinality, a quantity of it. Just how much stuff do you have? And then all of a sudden, that idea of a number, you have reality, which is actual stuff. But I have a number that helps me to deal with what I'm looking at. And that's one-dimensional space. I could take this and lift it up and say, well, what would two-dimensional space look like? Well, normally you take two-dimensional space. We have this. These are quantities, and I normally write this as x, y. What that really means, if I look at this, well, there's x there and there's y there, and it gets me to a particular location within this space. And I can do the same thing up to 3D. And I can have values in three-dimensional space, and I would have so many x's and then so many y's and so many z's, and it gets me to this x, y, z location. So space itself is just simply, in a way, it's like, where can you all go? And you have to get there for this to happen. Now, I end visualization at this point, because I can't visualize 4D. But I could take advantage of some cheaty things that we do. For example, this picture, if I make a picture like this, is that really three-dimensional? Obviously not. It's a bunch of lines on a two-dimensional space. But in your mind, you fill it in as if it's 3D because we have perspective geometry. Just the fact that we can do things like this, they had to develop math for this to work. Vanishing points, perspective geometry, and all these other sort of fun things. It's hard to do, to make it and draw it well. But it's a 2D representation of a 3D object. So we might do things like a three-dimensional representation of a fourth-dimensional object. Why? Because I can't represent fourth-dimensional objects. Because I just can't see it. What about fifth-dimensional? Can't see it. But on the other hand, could I talk about places in it? Sure, I just need to have what are your coordinates. But the coordinates are just a number, in a way, almost approximation, right? Because it's a physical thing. There's certain things you can't measure, right? There's irrationals and stuff like that can't be measured by fractions. So it's like, well, it's here. And we have an actual here. Now, but there's a different way of talking about space besides just physical location. Another way of talking about space is to simply look at things that I do in space. All of these are based upon location. But when I do things like with physics problems, location isn't the only thing we do. Like, how much do you have? Or quantity, how fast are you going? So if I had one car going 60 miles an hour and another car going 61 miles per hour and I say they hit, is this going to be devastating or not? Well, what if one's going 60 miles an hour and one's going 61 miles an hour right behind it and they hit? There's a 1 mile per hour tap. It's like, I think we could probably handle that. But if I said one was going 60 miles an hour and one's going 61 miles per hour, then they hit. What if one's going 60 and one's going 61? What if one's going 60 and one's going 61? Are there completely different effects for all of these situations? Absolutely. Now, the speed, which was like a single number representation, was the same between everything that I was using. What was causing the major differences? Direction. So there seems to be something in the real world where direction probably matters. And I have a quantity that I could represent it, and I just did with this, an arrow. It seems to be a natural representation. It exists within any dimensional space. I can draw arrows that are one-dimensional. I can draw arrows that are in two-dimensional space, three-dimensional space, whatever. But it seems like a very natural thing to do is, instead of location, what about direction and magnitude? And this would work with any dimension. And the easiest way to represent it would be just simply this. And the classic name that we call this is what? A vector. Now, so what is a vector? A vector exists within any dimension, from whatever you want, one dimension up to the infinite dimension, however high you want. And it's just an arrow in that space. What does it have? It has a magnitude this much, like 15 miles an hour, whatever degrees, whatever, and it has a direction that way. Now, just like we use metrics for things, metrics, single numbers, scalars are useful for things like what's the temperature, what's the energy, how much money do you have, what do you owe me, how tall are you? Those are all single-valued stuff. But all of a sudden we say that it's going that way this fast. or the temperature is increasing, like in this direction at maximum value. And so you would look at things like, oh, look at a plate. Heat is dispersing through the plate. If heat is dispersing through the plate, not only are there temperatures, there's a change effect that you would say, oh, look, there's increased temperature that way. It's decreased temperature that way. The temperature is the same in this direction. And so there's an idea of magnitude and direction for given problems. So it seems like this is a useful mathematical tool. Now, everything that we have is obviously just simply arrows. So this will become this thing that we call a vector. Is going to be our new mathematical toy. Right? What is going to be, so new toy, vector. Which is really just, it's an arrow in whatever space it exists. All right, what can I do with my toy? So what are some operations? First operation we are going to ask is, to you, if we would say a vector has a meaning of direction and magnitude, do you think that that vector is that vector? Is that vector? Is that vector? Do you think it really matters where it's at? It's kind of like the number 4. Think of the number 4. This 4 people is obviously different than 4 cows, but 4 is the same. That's a pretty big jump that occurred with them as people started using things like that. If you look at different cultures, they'll say things like, how big is this? And they would have to demonstrate this tall. And they would demonstrate tallness by moving their hand differently. If it was a person, you do this. If it's an animal, you do this. It's like, wow, because they're not the same. I have to use a different measure. And it's like, no, come on, it's the same measure. Are you okay with that? It's like, we loosen up the idea of a metric being a cardinal, which is separate from the object that the cardinal is applied to. And so that's what we're doing. This vector, yes, it has applications. A car is over here, a person's walking over here. But if I say it acts like a cardinal event, right, which is its direction and magnitude, I really don't care about location. So location doesn't matter. So sameness should be free of location. And what I should see is same direction and same magnitude. In other words, I don't care if we look at this guy. Look, this arrow is right here, but this arrow is over here. They're equal. Why? They're same direction, same magnitude. I don't care where they're located. Same direction, same magnitude. Period. That allows us to do certain things to help us on solving problems, especially when we're going to solve problems with, now that I understand sameness, what would it mean to, say, combine them and say, what do you think adding means? What would add mean? Well, the easiest way to do it is this is supposed to represent something that's real. So let's take a common example that you would do. This is person's vector 1, this is vector 2, and there are ropes. And I have a large weight attached to this, and I say pull. And so what are they doing? They're combining their pulls. Now, what do you think that this object sees? Will he see 2 vectors? No. This object, being blind, would see one larger vector, right? That would be doing what? Would he be pointing in that direction? Obviously not. Somewhere in between. And how will it pull? Well, what happens is it would pull in the same way. Get rid of the things I don't need here. And let's move you to this side. So that's still vector 1, right? It's acting as if vector 1 was sitting right here at the head of this guy. Vector 2 is acting just vector 2. Well, it's acting as if he's here, but he's actually at the head of this. So what's happening? What's happening is that I get this guy here, which is vector 1 plus vector 2. Addition of vectors acts according to the parallelogram law. In other words, I don't really care where. Yes, both of these guys are attached, but how is it acting? It acts as if vector 1 is rigid, and I attach the tail of one to the head of the other, and then the sum goes tail to head of the sum. And that's exactly what physically happens. If you would go out and do these measurements, and you'd have people pull and say, okay, what is this acting as a resultant? That pull. They will do the exact same thing. And so we would define addition to simply be exactly that. Another thing that you could do is what would happen if you start changing the magnitude. Like the direction stays essentially the same, but I say pull harder or pull less. In other words, you would have a vector, but I would say, what would happen if you would take some scalar amount of that vector? The vector will be in the exact same direction, but now this guy will be, if I stretch it out correspondingly, it'll stay in the same direction, it'll just get longer or shorter, but keeps the same direction. So what happens here is we change the magnitude by alpha, and if alpha is a negative number, you just simply flip direction 180 degrees. So you can imagine alpha is like a percentage. If it was 1, that means it's 100%, leave it. If it's 2, it's like 200%. If it's 0.1, 10% length. Negative 7, flip direction 700%, right? But it stays within the same parallel reference. And these are things that we do with vectors. We stretch them, and we add them. And we could combine those. Stretch this one, stretch that one, add those, resultant, as we go through it. These are things that you physically do. Now, obviously, this is all geometric in nature. How many of you would like to do all of your math from this point using straight edges and angles and geometry, and only geometry and no numbers at all? Just draw. And I measure this correctly. And that's, original mathematicians were geometers, right? More than they had metrics applied, but it was strongly analytic geometry. It was strongly focusing on it, including to the point that they would have compasses that were fixed. Like, I would want to bend this. No, you don't get to bend this. It's a stick that's tight. This is its fixed angle. And then you could make circles. But I need a circle of a different one. Good luck. How are you going to do that? All right, we had rigid rules on how things were applied. One of the big jumps to this was the analytic part, where we could apply algebra and numerics to this. One of the nice things of numerics to this is any vector for a particular space how can I use numbers? Because I have all these rules for numbers. I can take 2 plus 5. I can take 7 times 3. All this knowledge that I have for numbers, how can I use those to help me work with this? Well, vectors and numbers, if we would start off on 2D, which is the normal the typical, most primitive shape that we have, is what we do for a vector is given any vector at all. So that's vector v. For any vector at all, location doesn't matter. So if location doesn't matter, and I have a coordinate space that helps me figure out location, why don't I just go ahead and take this guy and move him so that the tail is always at the origin? Doesn't matter where it's at, so I'm just going to put the tail at the origin. If I put the tail at the origin, and that's true for all vectors, then the most defining quality of a vector is going to be the head, which will have two values, say x and y. And so then what would happen is vector v could be represented by the two metrics x and y. Why do I need two numbers? Because I'm in two-dimensional space. I still have one object, this arrow, but I need two numbers to represent it because I have to locate the head. If it's in 3D, we do the exact same thing. We take a vector, we put its tail somewhere at the origin. The head is what's of interest to us because that would uniquely define it. And so now vector v would be made up of x, y, and z, which is the coordinates of the head. Vector v is not those coordinates. Vector v is 0, 0, 0 to those coordinates. It's that arrow. And so I need to have three values. What's nice now about having these things in numbers is I cannot visualize fourth dimensional space. I cannot visualize 10th dimensional space. I can't draw that arrow because I can't see it. But who cares? If I talk about nth dimensional space, a vector is just simply made up of x1, x2, up to xn. It's an nth dimensional vector. So I can have a number representation. Life works. What does it look like? I can't draw it. But that would be where, if the tail's at 0, 0, 0, whatever, n zeros, the head's at those numbers, it's in between them. Okay, so if that's my number representation of it, let's go back to equality. What does it mean for vector 1 to equal vector 2? Well, here's where we're going to borrow what we've borrowed from matrices. When are two matrices equal? Same values in same positions. So instead of using v1 and v2, let's make, I suppose, probably a better notation would be, say, vector v and vector u. Is, well, if v is made up of v1, v2 up to vn, and u was made up of u1, u2 down to un, it would mean what? All those are equal. That actually kind of helps. If I would have an arrow over here and an arrow over here, are they the same arrow? Ooh, that's a good question. I have to line them up and physically move them. What's nice about this? Just look at the coordinates. If same values equal. So equality is trivial now. We just look at the numbers. The second thing, sum. What would be vector v plus vector u? What would that be equal to? Well, let's borrow matrices. How do you add two things? v1 plus u1, v2 plus u2, vn plus un. It's normal matrix addition. So vector addition is the exact same thing. Just add the coordinates. Will that form and here's one thing that you would need to do to yourself is, does that actually do this? Could you convince yourself that if you had the coordinates of this guy and you had the coordinates for this guy, that the coordinates for this guy are just his first coordinate is added, is that guy's first coordinate? And when you look at the parallelogram, the answer is yeah, because you go over, because they're 90 degrees to each other, right? It's how much over, how much over, how much up, how much up. And every dimension does that same thing. So yeah, that is the parallelogram rule. And then, what about scalar multiplication? What would be alpha v? So this is going to be alpha v1, alpha v2, alpha vn. It's the typical, that's why we're calling it scalar multiplication. It's scalar multiplication of matrices. So same thing, distribution rule. And then you would have to convince yourself, let's go back here, is that what that does? You take all these coordinates and you just simply multiply them all by the same number. Will it not change direction, and will it go out? Now, from this is actually our stuff. One of the things that does happen is, especially if you're in this world here and not the actual arrows, vectors are direction and magnitude. If I just gave you a bunch of numbers, we're eventually going to have to develop how much is here. If I just have all these numbers, could you figure out magnitude? And could you figure out direction or a concept of direction from this? We'll still have to build that up a little bit. Magnitude would be one where it's like, what do you think would do if we had all these numbers? Could we handle, can we get at least say magnitude? And we would write it, say, magnitude of v. What's Pythagorean's theorem for two-dimensional triangles? That's 90 degrees, right? What's Pythagorean's theorem? X squared plus y squared equals z squared, which would mean what's the length of z? Square root of x squared plus y squared. What happens if we go to 3 dimensions and we have go over this much, and then go up this much? And I need to figure out that length. Well, I don't have a triangle, I have 2 triangles. How would I get the base here? Well, this squared plus this squared is that squared. And then I have this squared, and this squared is this squared. But this squared is this squared plus this squared. So what have I just learned? This squared plus this squared plus this squared is that squared. And anyways, Pythagorean's theorem used triangle, 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 however how you want to go. It's just going to be the square root of v1 squared plus v2 squared plus everything up to vn squared. Eventually, we're actually going to loosen this up a little bit and talk about, are there any other ideas that I could talk about? Because in a way, this is distance, right? It's like, how far apart are these? And we'll actually talk about spaces where we loosen up the concept of how far apart are they? Can I find a thing that measures distance? And then can I find a thing? And then that's one question. That would be one example of it. And can we get an idea of direction? This is going to be later. We're going to need some work. Obviously, direction is going to have an issue, which is in relation to what? If you tell me that way, it's like, well, you're going to have to orientate me to figure out where you're, how do we handle pointing? You're going to have in reference to something as we go to it to understand where you can go and find places. So we're going to try to come up with some math that would give you number representations of that way and number representations of this much in terms of what's a magnitude and what's a direction, if we're given our problems not in terms of actual arrows, but we're given problems with just a bunch of numbers. This is the number representation of this object. Now, this also begins the first process of math where we have these concepts and they have physical representations, which is these arrow type of questions. So to get some idea of a space, at this particular time, to get some idea of a space where we're talking about, all right, if I do my normal two-dimensional space, three-dimensional space, four-dimensional space, or just restrict it to things I understand, three-dimensional space, I can visualize this in my mind. So it's this room. I can put a coordinate axis in this room. I can draw arrows that are going from my feet to the door. Right? There's an arrow that represents that, and that would be a vector. So it's this space that I'm operating around and I'm moving through. And these spaces are really, if I would look at it, I could imagine that this entire space could be considered that if my feet represent the origin and my, we're going left and right in terms of across the board and away from the board, and I have up and down here, I could imagine that every location in this space could be considered as arrows that start at my feet and then point away, like a porcupine. So you'd have this big giant nesting of arrows that are simply going out like that, and it gets you everywhere within that entire space. But that would mean that a space itself is really just simply a set of objects. The classic one we think about is vectors, right? Because they go from here to everywhere that you ever could get within your space. So my vectors start at my feet, and you have this porcupine effect that goes everywhere. It represents all of the things within all of the space that you're going. And I can somehow get around this space by taking vectors and stretching them, or taking vectors and putting them together to get a new spot. So I can take this one and this one. Oh, I'm now over here. And so we would go through it and say, if this is my world that I'm trying to consider, which is objects, and I'm going to go ahead and call vectors, two ways of moving, either stretching a vector or adding two vectors together to get to places. What I'm going to call a vector space is the following needs to work as I move around, right? And these things need to satisfy, let me see if I can count this right. I always get my counting wrong. So the book only lists 8, and there's actually 10 because they have 10, satisfy 10 axioms. Which is, what's an axiom? An axiom is something that's true. Why? Because it's true. It's not like we don't prove it to be true. This just is true. This needs to be true. So this is a known truth for a space of this nature. So I'm going to have a vector space if I have my objects, and I need two operators to find. I have a scalar multiplication object, which is the idea of somehow the idea of a stretch addition, somehow these two things combine. Now notice that on this, I might be using the word vector, but the moment I start here, what is a vector? That's like, I don't have to define it. It's just a thing. It could be students. It could be chairs. It could be a function. It could be a polynomial. It could be a matrix. It could be a form of math. I don't care. It's just a thing. It's a collection of stuff. Now, our natural application is these arrows. That's why we call them vectors. That's why it's called a vector space. But anything that satisfies these axioms will be a space of some sort. And it's the idea that I would like to go around in this space, but it satisfies these rules, which makes it a vector space. So the first two that we have to worry about are the closure axioms. C1 is simply that alpha v is in your vector space. Think of it this way. If you have a vector and you stretch it, it's still a vector. So let's say your objects are students, and I have a rule that says stretch, whatever it is. So I stretch a student. It's still a student. It wouldn't become a chair. Right? It's closed. Now, are all operators that you deal with actually closed? Can you do things to objects and make something completely else? Yeah, we've done it before. You could take like integration. That's a thing that happens to a function. If I would take the definite integral in particular, right? So if I say, what's the integral from 0 to 1 of x dx? You take that, okay, that's 1/2 x squared from 0 to 1. It's 1/2. What happened? A function went in, a number came out. That's not a function. A function became a scalar. That's not closed. I want to do things where a function becomes a function. Or a matrix becomes a matrix, or a vector becomes a vector. So I need closure. So if you stretch it, it still stays a vector. The second one is if you add them, it still stays a vector, whatever your object is. So if the things you're playing with are functions, if you add two functions, it better be a function. But that means you have to define what addition means, and you have to define what that thing means. What's a scalar times? You're going to have to define the operators for the space that you're talking about. All right, so that's the first thing that has to happen. All right, the next four are going to be the axioms on addition. The first one is if I would take a vector and add another vector, it wouldn't have mattered which order you did it in. In other words, we had the parallelogram rule. If you would go here and then here, it's the same thing as going here and then there, or going here and then there, it gets you to the same place. No weird sort of stuff happens. What law is this normally called? Commutative. Whatever your operator plus is, it needs to be commutative. Let's say your operator plus happened to be that you call function, if you would do functions, right? What if you did function, and I'm going to make a special plus g, and what it does is I'm going to take function f and then put function g underneath it. If I switch the order, which means switch the order, does it become something completely different? Yes. You just can't switch orders because the divide order matters. Who's on top, who's on bottom obviously matters. Same thing with subtraction, right? But so in other words, if you're going to make an operator called plus, it has to be commutative. Order shouldn't matter. Not only should it be commutative, what's this law normally called? Associative. It better be associative. Addition's binary. It only works on two things. So if you do the first two and then the third, or you did the last two and then the first, I don't care. Order doesn't matter. There's also an important feature that if you have commutativity and associativity, you can drop parentheses if everybody's plus. Why? Because it doesn't matter the order that you add. Not all operators have this, but you need it for a space like this. In other words, think about this idea of a vector space needs to be able to be moved through it. So if I go x then y or y then x, I don't care. It gets you to the same place. If I go x then y then z, well, how did you get there? I went y, z, then x combined. Or no, I went x, y, and then z combined. I don't care how the three go together. It gets you to the same space. It needs to be commutative and associative. That's what this law is allowing you to do. The third possibility of that is there is a zero object such that x plus the zero object is x. What must exist in your space? The additive identity. It's the additive do nothing. You need a zero object. Well, for normal vector spaces, what's a zero object? The all zero vector. Could you add, for example, if I take all zeros and I add it to x, y, z, what's happened? Nothing. It's still x, y, z. In other words, whatever your space is, you have to have a thing that does nothing under addition. That's your zero object. If you have a zero object, and here comes the fourth guy, for all vectors in the vector space, there is a minus vector such that the vector plus the minus vector is the zero object, which is called the additive inverse. So we would say these four things, say the following. The first two are, I don't care what order you do it in, first, second, third, any combination, associative, commutative. It's commutative and it's associative. Order doesn't matter for addition. The bottom two say that not only do you have a do nothing, you have a object that you can apply that becomes the do nothing. This plus some special thing. This is here. I might write it minus v, but the reason why I'm writing this is the additive inverse. Think of how do we do multiplicative inverse of functions? How do we composition inverse of functions? We would say, hey, I have a function, and what's its inverse? We would write what? Is that a power? No, it's a label. It's a label that under composition, this forms the identity, which is x, which is a function. This minus is not minus. This minus is a label. This is, hey, this guy is this guy's additive inverse. Why do we tend to use minuses a lot? Because it tends to show up in the undoing process. Like, for example, for the multiplicative inverse, what do you normally do? You reciprocal, which is a minus 1 power. For the additive inverse, what do you normally do? Multiply by negative 1. Right? What's 5's additive inverse? Negative 1 times 5. What's negative 7's additive inverse? Negative 1 times negative 7, which is 7. Right? But it's that minus keeps showing up naturally. So that's why we usually use it as a label. All right, and then the next four. So these first four are on the addition axioms. The next four are going to be based upon the scalar multiplication axioms. And so this will be A5, A6, A7, A8. A5 is alpha times V plus U is alpha V plus alpha U. A6 is if you had alpha plus beta v, it is alpha v plus beta v. I'll call it distributive number 1 and distributive law number 2. Why do we need to have two types of distribution? Here's a question. Look at that symbol and look at that symbol. What does the top symbol represent?
Vector addition.
Vector addition. It's vector plus vector, which means that you've done this sort of object. What's the bottom plus? Scalar addition, which is not vector addition. It's number plus number. Like, what's 5 plus 3? 8. Right? It's completely different pluses. Completely different. We need two different distributions because we have different operations. We have, what's the possibility of, what could happen? I could add vectors and then try to stretch it. What is this one? Well, I have two scalars that need to be worked with and then use that to stretch a vector. And that says, well, just stretch the vector by the first, stretch the vector by the second, and then add those two vectors, and it goes to the same place. So it's two completely different questions. That's an important part of position in terms of the symbols. So we have two types of distribution. Then we could say things like, well, what if I had an alpha times a beta plus a vector? This says I have no operator right there, but that no operator is scalar multiplication. I have no operator right here, but that is a scalar times a vector multiplication, which is distribution, right? Everybody gets that alpha beta. So even though they're not even there, they're completely different operators. And what is this? Well, you could take the vector and stretch it by beta, find that, and then stretch it by alpha. And then honestly, you could flip the order because though normal scalar multiplication is commutative. So I could actually stretch by alpha and then multiply by beta. And then the last one, which is a form of association, but not really. I mean, it is associative. And the last one is this. If you take the number 1 and you multiply by a vector, it's still the same vector. Which is a form of multiplicative identity. Obviously, there is no multiplicative inverse. Why would there no be multiplicative inverse? Because 1 is not a vector. Inverses require closure. This vector with this vector spits out the inverse. Sorry, spits out the identity. Well, no vector with another vector would ever spit out the number 1 because I need closure. Vector, vector, vector. So there is no such thing as an inverse, but there is an identity. So there's a multiplicative identity. Multiply by 1, nothing happens. So what happens now for this? If you're given a set of objects, normally you call it V, and two operations, which would normally be, say, alpha V and then, say, V plus U, and all 10 axioms hold. Call this a vector space. So it's a set of stuff. You come up, for whatever reason, with two operators. One's a stretching operator, and one is an addition operator, such that all 10 things hold. It's going to be a vector space. The purpose of a vector space is to be able to get everywhere within it. Let's try a strange one. I'll start off with this. obviously R2, which is 2D, R3, which is 3D, Rn, which is nth dimension, are all vector spaces. Check. What are we doing? We're using the normal scalar multiplication. In other words, just use your normal scalar multiply and vector addition that we had, and you could verify all of those things work. You would go through each of those. And now this is where it might seem like a little bit of a grind. For example, how would you show that for three-dimensional space? What's x? x1, x2, x3. What's y? y1, y2, y3. What's z? z1, z2, z3. And what do? I take y1, y2, y3 and add z1, z2, z3, which is y1 plus y1 plus z1, y2 plus z2, y3 plus z3, and that's a new vector. And then I'm going to add x1, x2, x3, and when I add that, it becomes x1 plus y1 plus z1, and then do the same thing on the right-hand side, and you'll notice, oh, look, they're equal. And you have to do it for every single problem. Except one of the things that you sometimes have to figure out in a little bit of a creative way is, what do you think the zero object is? Does it have a zero object is important. Sometimes you'll have an introduced, and that's like, wait, we don't even have a zero object. Well, now you have a problem. You're not going to have a vector space. Why is a zero object important? It's your origin. This is where we have the beginnings. If you don't have a zero object, you don't have something to begin with. So let's take one that's a little bit odd. So V is set of all continuous functions over a closed interval AB. So here's an example. There's A, there's B. What's a continuous function? What's a layman's definition for continuous function? You put your pencil down, and you're not allowed to pick it up until you get to the other side. It's continuous. No holes, no jumps. Has to be a function, so I don't get to do that. All right? Doesn't pass the vertical line test. That's bad. So that is a continuous function. So this would be, guess what? V. I'll call him V1. Could you think of another continuous function? How about I start here and I go down and back up? I'll call him V2. What am I doing? All. Are there a lot? Yeah, there's an uncountably infinite number of these things. It's like, where can I start? Anywhere. Where can I end? Anywhere. What am I going to do? I'm going to draw some curve. Where can it go? Anywhere. And so my space is all of them. I mean, it would almost be, if you imagined all of them, it'd be like a solid wall, right? Just every possible point that would ever exist between A and B, there's a curve that somehow goes, and that's one of those functions. I want all of those functions. So that's my space. Now, now comes the question of, all right, that's my stuff. Now I need operators. So this is obviously just some function. I'll call him f1x. This is obviously some function. I shall call him f2x, right? They're functions. It's a continuous function over this interval. Now I have my stuff. Now I need two operators. I need to stretch, and I need an addition. What do you think would be a good definition for a scalar multiplier? All right, what am I dealing with? functions. Can I just go ahead and put a number in front of a function? Can I just go ahead and, we're just going to go ahead and define this to be alpha f of x. What does that do? What's f of x? It's a real number. It's the height at this particular point. What's alpha? It's a real number. What's alpha times f? It's just a normal number multiply. What would it do to a function? When you multiply a function by an alpha, it simply stretches it away from the origin. In other words, it grabs a hold of it and pulls it. What if it's by 2? Everybody stretches by 2. What if it's by -5? Flip it over, stretch it by 5. What if it's multiplied by 0.1? It'd be a stretch, but it'd be a compression, right? Squeeze it, all the heights become 0.1, their old height. So all I'm doing is taking every one of these. So what does this do? It stretches it. It's the normal stretch function. I just simply grab it and pull it away from the x-axis. That's what's happening. Now, what do you think would be a good definition for adding functions? How about adding functions? Say f1 of x plus f2 of x. Seem useful? Am I allowed to add functions? Absolutely. What does it do? It adds their heights. So, for example, if I added these two functions, what would it do? These numbers are all, what are these heights? Negatives. And so you would go like here, like this, that would be this, and that would be this height. And what am I doing? This height, that's a negative number. It's going to what? Drop it down to there. Just adding heights. If they were both positive, it would lift. If they're both negative, they would both drop. If one's positive and one's negative, it's going to calculate the difference by subtraction of heights, right? So is that going to, now comes our question. That's my definition. So now we need to get to check. That's what I believe the operators I want. Now, is this a vector space? We need to check. C1 is alpha f of x a function? Like everybody can agree, yes. Right? C2 is f1 of x plus f2 of x a function? Yes, that's also true. Actually, when we in college algebra, what function is that? What do we normally call that? That would be the f1 plus f2 function. So yes, it's a function. So we at least have closures. We're not doing anything weird. Grab the heights, stretch it, that's still a continuous function. Grab the heights, add them together, that's still a continuous function. There's no problems that are going to show up. And now we get to move on the operator axioms in terms of A1 to AA. A1. F1 plus F2 of x is what? That was F1 of x plus F2 of x. But that's a real number, right? Once it's been evaluated, it's a real number. That's a real number, so what's that plus? It's real number plus. Does that allow you to do this? Yes. And function plus function is function plus function. Is it commutative? Yes. A2. What if I would have function 1, but then I had function 2, function 3 as a function? What does that mean? That means that this would be, eventually, I'll skip some steps. That'd be f1 of x plus f2 of x plus f3 of x in parentheses. But these are real numbers, right? These functions are the plus of functions. These numbers are the addition of reals. Reals are associative. Which is just simply f1 plus f2 plus f3 as a function. So yeah, it's associative as well. Why? Because addition of real numbers is associative. We're taking advantage of that. A function spits out reals. A3, we need a zero function so that a vector plus 0 is still the vector. I need a function. I think I'm going to go ahead and call my 0 function. I'm going to call him z of x. I need a z of x so that a function plus my z is still just plain old f of x. But what is f plus z? That's really f of x plus z of x is supposed to be f of x. Now we take a long pause. What is the only way for this to happen? Z of x has to be 0. Is this a function? Yeah. What does it do? What does this function do? It maps all numbers to what? 0. If it would look at, what would be its plot? If that's a and b, what's z of x? That's z of x equals 0, right? Just no height. Is that a continuous function? Absolutely. What happens when I add no height to any function? I'm pretty sure it leaves that function alone. So there we have it. So yep, I have a 0 function. It's just 0. It's the function of no height. Add no height to any other function. That other function stays alone. No bad things have happened. It's f of x plus 0 is still f of x. That's obviously true. Now comes another question. We need additive inverses. So if I took f of x plus his inverse, and it needs to spit out 0, because that's z of x, which is a function. What would, if I don't know what number this is, but if I take a number, what should I add to it so it always spits out 0? The negative of that number. And so it ends up being that, you know what? I bet f of x plus a minus 1 times f of x is 0. And so this is our additive inverse. What did I really do? Think about this. You have this function right here. If I would add, I would take this function and flip it over down below like this. What happens if I add those two? It would simply become the 0 function. Is everybody okay with that? So hey, just put it on the other side of the real number line. That's all that says. Add those two. So everybody has an additive inverse. Flip it across the x-axis. It's will always add to 0. So that's the unique additive inverse. Okay, so those axioms hold. On to A5. Now we talk about the scalar multiplication rules, which is alpha and then one function plus another function. Well, as a function of x, this is obviously going to be alpha f1 of x plus alpha f2 of x. Probably should not skip the one step in between here. This is alpha times what? f1 of x plus f2 of x, which is equal to alpha f1 of x plus alpha f2 of x. Why? This plus is function plus. This plus is what? Real numbers. And so now I have alpha times real plus real. Oop, normal distribution law applies. It distributes. So yes, that holds. A5. What if I would take an alpha plus a beta and then have f1 of x? Well, f1 of x is what? It's a real number. So it distributes from the right. And that becomes alpha f1 of x plus beta f1 of x. So, yep, those work as well. Yes?
A6.
Thank you. Seven. Alpha beta f1 of x is going to be alpha beta f1 of x. Why? What's that? Real number, real number, real number, real number. Ah, the associative property of real numbers, we're good. Still works. And finally, A8. What's the number 1 times f of x? I'm pretty sure it's f of x. Woo! All right. So this is a vector space, and things that end up being special usually get their own name, and use CAB to represent it. What's the capital C mean? Continuous. What's AB? It's over AB. What is it? It's a set of all continuous functions over AB with the normally defined. If they do not state what the operators are, you fall into the normal descriptive operators of the book, which is normal scalar function multiplication, normal function plus function multiplication. So this is a space. And again, what's the point of spaces? Getting everywhere. And it also ends up being that I can get places by doing what? Taking a continuous function, stretching it, taking a continuous function and adding it to a continuous function and getting another continuous function. And it's commutative, it's associative, it has a addition identity, it has an addition inverse, it has distributive for both the functional add as well as the scalar add, both distributions. It has the 1 times a function is a function, and it has the associative property. All of those hold, which basically says, in a way, it's a nice space. It's a space that allows you to move around in some rather nice ways. You can do it in a lot of ways smoothly as they work out. Other spaces that you can play around with all right. What is this? This space was imagine between A and B every possible continuous function at all, and imagine how continuous functions interact to make new continuous functions. What's this space? This space is the space of all m by n rectangular blocks of numbers, matrices. And so what do? I think about it this way. It's like, okay, what is your space? It's not a space. In the same way you think of the idea, like here, and when I normally say space, we usually think of physical interacting space and moving around in 3 dimensions. What we're talking about for continuous functions. Functions that become other functions, and what are all the ones that we can make. What's this one? What's my space? Every possible m by n block of numbers. What does that include? All of them. And so I imagine that is like almost, I can write it in its entire boundary. So I can talk about 5 by 4 matrices. I say, that's my entire space. What are all 5 by 4 matrices that you ever could possibly do? And then what you then define is the operators. That obviously alpha v is the normal scalar multiply of matrices. And obviously v1 plus v2 is normal matrix addition. And you have to check all 10 axioms. So one way of looking at this is I can make, let's say we talk about 5 by 4. All 5 by 4 matrices can be considered as a matrix stretched, or a matrix plus another matrix, or a bunch of those done. Take one matrix and stretch it, take another matrix and stretch it, take another matrix and stretch it, add all those together to get this new matrix. And so you can think of every possible matrix as this idea of stretching, which would be multiplying it by a scalar, and addition makes new things. Pn, which is n-term polynomial space, actually I sit on this one. Who do you think the 0 object is for matrices? Big O, right? The big O would be the 0 object. For n-term polynomials look like this. A polynomial that has n terms would start off at, say, a0 plus a1x plus a2x squared plus, how high do I go? X to the n minus 1. Because what's my lowest? X to the 0, and then x to the 1, x to the 2. You go up to the x to the n minus 1 degree. And so this would be a sample object of n-term polynomial space. And what do you think addition is? How do you add polynomials? You add like terms. How do you multiply polynomials? Well, we don't need multiplication. We need what? Scalar multiplication. And what's scalar multiplication? You just stretch each of the coefficients. What do you think the 0 object is? Every coefficient is 0. It's 0, 0x, 0x squared, 0x cubed, up to 0x to the n minus 1. And so taking all of that, all the axioms apply, this now becomes my space. Please generate polynomials. And doing things like this becomes important because we're interested in making such objects. One of the ways that we're going to talk about this is the fact that this is the beginning of a scaffolding process. What I would like to do is if everything can be built by stretching and adding, can I have the most primitive objects possible, and then from those, stretch and add those to make everyone? In other words, what do we do in Calc 3? I talk about I, J, and K. And then I, J, and K are stretched and added to get to any vector at all. And that's what we'll do. In any space, what's the most primitive tools we can take and stretch those and add them to make all of the others. So I can represent the entire space with as few of things as possible. And that'll be our goal. That's why we were interested in these spaces and these operators. All right, that's it.
Mm-hmm.